Yes, sir.
Okay. I think one of you have to, yeah, it started recording, correct. Fine. So in the previous class, I stopped it somewhere over here, right? So we started with the analysis of a fixed bias circuit. Okay. So analysis of fixed bias circuit based amplifier. The capacitors were given because it is an amplifier circuit. So in case of an amplifier circuit, you will have the capacitors. So, the task of these two capacitors is to block DC signals, right? Because capacitors offer infinite reactance to, DC current, and it offers finite reactance to AC current. Hence, it isolates DC conditions. Okay, because amplifier operation is purely AC operation and biasing operation is purely DC operation. All right. So with that note, we could isolate DC conditions. So how do we do it? We ground VCC to 0, right? And we also replace all capacitors with short circuit equivalents, because for AC circuit, right? So for AC circuit, let me write here. This is for AC circuit. Okay. So by doing that, what we get is something of this kind. Yeah. So by applying step number 1 and step number 2, we get something like this. And finally, you need to insert RE model in place of the transistor, right? Now, in this circuit diagram, it is pretty clear that the transistor is placed in common emitter configuration. Hence, common emitter configuration RE model needs to be substituted. So the blue objects, whatever you are seeing in your figure 2. Okay. In figure 2, whatever blue objects you are seeing, they belong to the RE model of CE transistor. All right. Okay. Now, sometimes in problems, they will also ask you to consider R0. Okay, what is R0? R0 is output impedance. Output impedance of CE RE model. Okay, CE RE model. So that means to say, if asked, you can place this R0 somewhere between collector and ground. Okay, so something like this you can place. Okay, since there is space crunch, what I've done, I've just dragged the terminal of R0 somewhere over here. So this is my R0. Let me write here. This is R0. Okay, fine. Okay, now let's go ahead with the performance parameter. Okay. Any doubts in this? How to get the RE model? Did you understand? Okay. If you give me green signal, then only I can go ahead. Okay.
Yes, sir.
Yeah. All right. Fine. So performance parameters. Firstly, let us start with Zi. Okay, Zi. So Zi is defined as the input impedance, and equation for Zi will be Vi by Ii. Okay. Vi is the voltage which is applied across base to ground. Okay, you can clearly observe Vi over here. Okay, and II is the current which is getting into the transistor network. Okay, remember one thing. Can anyone tell me, is II equal to IB? Can anyone tell me? Is II equal to IB? No, right? That's because there is a base node here. So what happens is that, there will be a flow of current Ix through the base resistor. Okay, so if I were to apply KCL at node B, what I get is input current as II and output current as Ix plus IB. Okay, Ix plus Ib. Of course, for approximation's sake, you can always consider this Ix as small. Okay, that's because normally base resistor is very large. That's okay, nevertheless. So that's the reason what I'm telling you over here is that don't apply KVL. Okay, don't apply KVL to find an expression for Vi and Ia. No, we don't apply KVL over here. You know, just by inspection method, we are trying to extract what is that impedance, you know, you are going to get when you look into the network. So when you look into the network from input port, you see that there are two resistors connected in parallel, right? And both of these resistors, okay, being connected across base terminal and the ground terminal. So by inspection method, you can straight away write your input impedance Zi as parallel combination of RB and beta RA. All right. So parallel combination of RB and beta RA. So that's your input impedance. Okay. So fine. So that's about your RB and beta RA. Where once again I want to point out that RE can be found from the following expression, that is 26 millivolt divided by capital IE. Remember, this is DC current. Okay, DC current, and this current you need to find from the biasing circuit. Okay, so that current capital IE needs to be found from the biasing circuit. Okay, fine. So over here itself, let me introduce you to something known as approximation. All right, approximation. Okay, so approximation says that if the base resistor RB is greater than or equal to 10 times beta RE. Okay, so this is the condition. If base resistor RB is greater than or equal to 10 times beta RE, then you can say that RB is very large compared to beta RA. Okay, what happens when you have a very large resistor connected in parallel with a smaller resistance value? What will happen to the equivalent resistance value? Can anyone quickly tell me? Or rather, I put it in this way. I have 400 kilo ohm resistor connected in parallel with 1 kilo ohm resistor. So what will be the equivalent resistance? My question is, I have two. One is 400 kilo ohm resistor and R2 is 1 kilo ohm resistor. Okay, these are very helpful in your competitive exams and all. Okay, wherein you will have to find the range. So when these two are connected in parallel, your equivalent resistance, okay, will be very close to the least resistance among the lot. What is the least resistance among the lot? That is 1 kilo. So it is slightly less than 1 kilo. So similarly, when RB is extremely high compared to beta RE, so your input impedance is approximately equal to beta RE. Okay, input impedance is approximately equal to beta RE. Of course, you can apply this approximation provided you take care of this particular condition. Okay, this is your condition. Okay, fine. That's your input impedance. Approximate expression I have provided, and also I have provided the exact expression. Okay, next up we have Z0. And what is Z0? Z0 is called as the output impedance. So output impedance by definition is the ratio of output voltage to output current. But once again, I'm not going to apply KVL in the output circuit. Instead, I use inspection method to determine the output impedance. Okay, now look from the output side and tell me, okay, first of all, you need to identify the output ports. The output port going to be the collector terminal and the ground terminal. So across collector and ground, what resistors are coming in contact? Can anyone tell me? Across collector and ground, what do you see from the output side? You see that RC, is getting connected in parallel with R0. So when you calculate Z0, you would see that, R0 is getting connected in parallel with RC. Okay, so that's your output impedance, R0 parallel with RC. Okay. However, this is your exact expression, but quite often what happens is that, the value of R0 is way bigger than RC, due to which, your Z0 approximately becomes R0 itself. So let me apply the approximation condition. Okay, approximation condition. Approximation condition says that if R0 is greater than or equal to 10 times RC, okay, you can say that R0 is way bigger than RC. Therefore, Z0 approximately becomes RC. Okay, Z0 approximately becomes RC. Okay, you want me to show you with an example? Okay, example, in your RE model, normal range for R0 is about 40 kilo ohm, and RC is always, in the range of a few kilo ohms. So, say a typical resistor of, say, 2 kilo ohm, let's take. Okay, and you try to find out Z0. So Z0 is 40 kilo ohm into 2 kilo ohm divided by 42 kilo ohm, right? So just take out the ratio and tell me how much you'll get it. So it is okay. You will get it as 1.9 kilo ohm. Okay. Did anyone get it? Z0 as 1.9 kilo ohm.
Yes, sir.
So that means to say Z0 is equal to 1.9 kilo, which is very close to, the RC value, which is 2 kilo. So that is what I am trying to convey over here. Okay. All right. So that's your Z0. So exact expression and the approximate expression, both expressions we have derived. Okay. Next up, we have the voltage gain, AV. Okay. Voltage gain AV. So how do we find voltage gain AV? So voltage gain AV is found using the formula V0 by Vi. Okay. So there is no direct or inspection method to determine voltage gain. We need to calculate what is V0 and what is Vi. Okay. So if you have V0 and Vi expression, and probably you can divide the two to get the voltage gain expression. All right. So first let us write what is voltage gain, output voltage V0. Okay. So let's go back to the circuit and let's try to find out what is V0. Okay. So what is V0 here? V0 is the voltage measured from collector to ground. Correct. Voltage measured from collector to ground. So V0 can be written as I0 into the resistance RC parallel with R0. RC parallel with R0. Okay. Now, one thing is very, very important. Okay, is the current direction of I0. You see, the current direction of I0 is kind of inward current direction. Okay, if you were to consider, okay, the inward current direction, the polarity, okay, of the output voltage, will come something like this, right? Flipped manner. So I0 fixes the polarity given by the orange color. However, the actual output voltage polarity, we have taken it as, in the opposite sense. So basically, this voltage V0 needs to be tabulated with a negative sign. Okay, simply because current I0 gives the opposite polarity output voltage. Okay, that's your I0. Okay, and I0 is nothing but IC. Okay, I0 is nothing but IC. Therefore, you can write V0 as minus IC into RC parallel with R0. Okay, so that's your, say, expression 1. Okay, now let us go to VI. Okay, so VI, you can write it as VI, you can write it as II into ZI. Or, okay, or you can also write it as IB into ZI. Okay, two equations are possible. Okay, what is VI? What is VI? Voltage measured from base to ground. Okay, so voltage measured from base to ground. Okay, let me just recreate the scenario. Okay, here let me spend more time in clarifying the things, because this is very, very crucial to understand the future circuits. Okay, what do we have here? We have RB and we have beta RA. Okay, and this node is anyhow, it is grounded. This is my base terminal. Okay, and this I'm going to take it as II. All right, and this I'm going to take it as IB. Okay, now observe carefully. Voltage VI will come across RB, as well as it will also be coming across beta RA, because it's a parallel circuit. So measuring voltage from here to here is same as measuring the voltage from this node to this node. Okay, hence I can write VI as II into ZI. Okay, what is ZI? ZI is this whole stuff is ZI. Okay, this whole thing is ZI. This whole thing is ZI. Okay, so I can write VI as II into ZI, or I can also write VI as, you know, IB into IB into beta RA, one and the same. Okay, did you understand this particular point? I want to take this particular expression because when I divide the two expressions, okay, what do I get? In the numerator, anyhow, I have IC. In the denominator, I will get IB, so that I can take the ratio IC by IB as beta. Okay. Now, if I were to take the input current as II, then I cannot write a straightforward expression for IC by II, right? Because there is no expression which defines the ratio of IC divided by II. Okay, because II is different, IB is different. Okay, II is slightly greater than IB. So that's the reason what I will do on the input side. I will write my input voltage expression in terms of the base current IB. All right. So VI is IB times beta into RA. Let me take this particular expression as 2. Now let me find out the voltage gain. V0. What do I have against V0? I have minus IC into RC parallel with R0 divided by VI. What do I have against VI? I have IB into beta RA. Okay, or the ratio, you know, IC by IB can be written as beta. So you have minus beta into RC parallel with R0 divided by beta into RA. So beta gets cancelled, hence you are left with AV is equal to minus RC parallel with R0 divided by RE. So this is the expression for voltage gain. Okay. Remember one thing, the negative sign indicates that there is 180-degree phase shift. As expected, right? In the very beginning I mentioned, common emitter configuration always gives 180-degree phase shift between the input and the output. Phase shift between VI and V0. Okay. So approximation. Okay. So in approximation, you have already seen that if your R naught is 10 times greater than RC, you can write RC parallel with R naught approximately RC itself. So your approximate, voltage gain expression can be written as minus RC divided by RE. RC divided by RE. Okay. And if load of RL is connected across the collector to ground terminal, then AV is given as, can anyone tell me, if a load of RL is connected across collector to ground terminal, then what would have been the gain? Can anyone tell me? It's something like this. Just redrawing the output circuit scenario. Okay, so this is your beta IB. Okay, so this is your R naught. This is your RC. Okay, so what I'm saying is, let's say load resistor RL is connected, okay, across collector and ground. Then what will be the expression for voltage gain? Can anyone tell me? What will be the expression for voltage gain? What is V naught? V naught is always minus I naught into Z naught. And what is Z naught here? For Z naught, you have 3 resistors connected in parallel. So Z naught going to be R naught parallel with RC parallel with RL. Yes. So this is how we calculate. Okay. You don't have to worry about what kind of resistance is connected. Is it a small resistance or large resistance? Doesn't matter. Okay. It is always going to be a parallel circuit across the output side. So basically 3 resistors gets connected in parallel. Okay. So that's how we calculate the gain. So your voltage gain, exact expression for voltage gain going to be minus R naught parallel with RC parallel with RL divided by RE. So this will be the expression if you have any load connected across collector and ground. Okay, fine. So that's your voltage gain. And finally, we have our current gain AI. So current gain AI is given as I naught by II. I naught by II. Okay, where I naught can be extracted from your output voltage expression, right? What is I naught? I naught can be given as minus V naught by Z naught, because we have already seen V naught is negative I naught into Z naught. So I naught is minus V naught by Z naught. Okay. And that can be written as minus V naught divided by, what is Z naught? Okay. Z naught is RC parallel with R naught. Okay, I'm not considering the load resistance. If load resistance is there, you can also include RL over there. All right. And also we have II. II is nothing but input, voltage divided by input current. Okay, fine. So let us find, AI. AI is I naught by II. Okay, what is I naught? We have minus V naught by Z naught into II. What is II? It is basically VI by ZI. Since it is coming in the denominator, it is ZI by VI. Okay. Now let me rearrange the expression in such a way that I get the voltage ratio. So V naught by VI. Okay, into the ratio of 2 impedances, ZI by Z naught. Okay, Zi by Z0. Okay. So what is this expression? Can anyone tell me? V0 by Vi. What is this expression? This expression is the voltage gain, output voltage to input voltage. Okay. So negative V0 by Vi is AV. So what you can write is, you can write your current expression as AI is equal to AV times Zi by Z0. Okay. And remember, the current gain is dimensionless because voltage by voltage, unitless, is impedance by impedance, again unitless. So this is dimensionless. Okay, that's how we calculate the current gain. So current gain can be simply calculated by taking out the impedance ratio, input impedance to output impedance divided into the voltage gain. Okay, Zi and Z0 is already being found in the previous steps. Okay, all right. So this is the concept of calculation of performance parameters. All right. Now what let me do is, let me quickly solve a problem on common fixed bias circuit. Yeah. All right. Take down the question. For the network shown below, determine the following. RE, Zi with R0 equal to infinity ohms. Third one, Z0 with R0 equal to infinity ohms. Fourth, AV with R0 equal to infinity ohms. Okay. Fifth one, Z0 and AV with R0 is equal to 50 kilo ohms. 50 kilo ohms. Okay. And compare the results. Okay. So this is the circuit. Okay, so R0 is given 50 kilo ohm, RB is 470 kilo ohm, RC is 3 kilo ohm, and this is the base, collector, and emitter terminal, and you also have been given with the capacitor values, 10 microfarad each. All right. This is your Vi, and this is your V0. Okay. All signal measurement is done with respect to ground. Okay. Whether they show ground terminal or not, you should understand that Vi and V0 is always measured with respect to either base and ground or collector to ground. Okay. Fine. So this is the circuit diagram. This is the circuit diagram. Okay. So first we need to construct the RE model. Okay, remember one thing, this particular question can be asked with emitter bias or voltage divider bias. Okay, the method remains the same. Normally this particular question comes for 8 marks to 10 marks. Okay, so this is how the marks are distributed. Okay, first you have to construct RE model. So this RE model will get about 2 marks. All right. So RE model you construct. You don't have to write down these steps, okay, such that ground, VCC, short circuit capacitors. Directly you can apply those steps. So what I will do, I will short circuit the capacitors. SC is short circuit the capacitors. Okay. Next, ground VCC. Okay, and then let me reconstruct the circuit. Okay, then let me just redraw the circuit. Okay, so this is what you get when you redraw the circuit. So this is your base terminal. This is your beta RE. Okay, I'm just placing the RE model also. Okay, this is your beta RE, and then comes the external biasing resistor RB. Okay, so this is where you feed your input VI minus and plus. This is your II, and this is your IB. So that's on the input side, and on the output side you have the controlled source beta times IB. Okay, and the collector terminal. Okay, and you will also have the output impedance of RE model, small r0, and then the collector resistor. Okay, RC. Okay, so RC is 3 kilo ohm. Let me write down the value, and RB is 470 kilo ohm. All right. So this is my RE model. So what I will do to add, better clarity, let me place the RE model element inside this box. Okay, this is my RE model for CE mode, common emitter mode. Okay. Did you understand? Can I go ahead?
Yes, sir.
So this is my V0. All right, fine. First one, let us find out RE. So first task is to find effective AC resistance RE. So RE is calculated as 26 millivolt divided by IE. Okay, so this IE I have already told you. Okay, I capital E capital, right? So this is DC current. Okay, so how will you find DC current? You can find DC current provided you know the biasing circuit, right? Now we have already seen in module 1 that for a fixed bias circuit, your base current IB is basically VCC minus VBE divided by RB. You see, module 1 will not leave you until you reach module 5. Okay, till module 4, you will be pulling the concepts from module 1, module 2, so on and so forth. Okay, fine. So IB is this. Okay, once IB is known, you can find out IB, correct? So IE is 1 plus beta times IB. So this is the whole idea behind calculating IE. Okay, so what's VCC? VCC is, let me go up, okay, 12 volts, right? So VCC is 12 minus VB, given or not given, let us assume silicon transistor, divided by RB. RB is 470 kilo. Okay, here I want to make a point. If given, you take the respective transistor, whether it is silicon or germanium. If not given, always assume silicon transistor. Okay, don't become aggressive and don't take your germanium or gallium arsenide. Okay, because in the scheme, almost all the times they will take the VBE potential as 0.7. Okay, so please take it as silicon if the type of material is not mentioned. Okay, so what do you get IB as? Okay, IB, do you get closer to 24 microamperes? Did anyone get it? Are you getting it? Nirja, are you getting it?
Yes, sir.
Okay, fine. So IB is 24, and what is IE? So it is 1 plus 100 into 24.04 microamperes. So it is about 2.4 milli. Okay, so 2.428 milli. So IE is 2.428 milliamperes. Milliamperes. Once IE is known, you can find out RE. RE is 26 millivolt divided by IE, that is 26 milli divided by 2.428 milli, 10.71 ohms. 10.71 ohms. So that's your RE. Okay. Let us cut it off. So RE is found. Okay. So this step will fetch you, say, 2 marks. Okay. Next we have Zi. Okay. So you need to determine Zi with R naught is equal to infinity ohm. Okay. Trust me, R naught is found on the output side, so it will not have any effect on Zi. Okay. This is just to confuse you guys. They have given find Zi under the impression that R naught is infinite ohm. Doesn't really matter because Zi is found on the input side. So what is Zi? Zi we have already seen in the previous analysis that Zi is parallel combination of RB and beta RA. Yeah, so this is Zi. Let me mark. Okay, as you when you look into the network, you get to see the Zi. Similarly, on the output side, when you look into the network, you would get Z0. Okay, so Zi is RB into beta times RA. That is equal to, okay, RB is 470 kilo ohm. Okay, into beta is 100 into RE is 10.71. Okay, divided by 470K. Okay, plus 100 into 10.71. Okay, beta is 100 and RE is 10.71 ohms. So how much will you get Zi as? Because you can clearly observe that RB is very, very big compared to, beta RE. So obviously your beta RE, sorry, Zi should be very close to beta RE. By inspection method only I can tell. You just find out and tell me what do you get overall input impedance Zi as. I think you'll get it as 1.07 only. Correct? Can
Yes,
anyone? Yeah, quickly confirm. Yeah, fine. So that's your Zi. Okay, you can see that. Let me write a proper comment over here. Very close to beta RE. Okay, that implies your Zi is approximately close to beta RE. This is what we had predicted, right? If your RB were to be 10 times greater than beta RE, then your overall input impedance will be very close to beta RE itself. Okay, this is what is the end result. Fine, so that's your Zi. Next, third one, what is it? Z0 with R0. Okay. Z0 with R0 is equal to infinity ohms. Okay, Z0 with R0 is equal to infinity ohms. That means to say, okay, first let me write the exact expression for Z0. So Z0 is RC parallel with R0. Okay, Z0 is RC parallel with R0. So that implies 3 kilo ohm is connected in parallel with an infinite ohm resistor. So what is the output impedance then? Can anyone tell me? 3 kilo ohm itself. Okay, 3 kilo ohm itself. So output impedance is 3 kilo ohm. Why is that so? Because when you have two resistors connected in parallel, one is having low resistance value and one is having extremely high resistance value. What happens is that current flow through this infinity ohm resistor is 0. So it gets isolated from the circuit. Hence, you will be left with only the finite resistance resistor, which is 3 kilo ohm resistor. So that's your Z0. Third one. Okay. And fourth one is AV. okay, with R0 is equal to infinity ohm. Okay, so expression for AV, okay, let me just rewrite the expression, is minus I0 into Z0 divided by IB into ZI, or minus I0 is IC and Z0 is RC parallel with R0 divided by IB into beta RA. Okay, so you know that IC by IB is beta. So this beta and this beta gets cancelled. So AV is minus RC by R0, sorry, RC parallel with R0 divided by RE. Okay, so we have already seen that when you have an infinite ohm resistor connected across RC, your output resistance becomes RC itself. So basically voltage gain in this particular case going to be the ratio of collector resistor to AC effective resistance RA. So that's minus 3 kilo ohm divided by 10.71 ohms. So how much will you get? AV as around minus 280.11 you'll get. That's the textbook answer. So that's your voltage gain under infinite output resistance. Okay, now let us find out fifth part, right? Fifth part. Yeah, fifth part, what is that we should do? We should find Z0 as well as AV with R0 is equal to 50 kilo ohm, right? So let's find out Z0 with R0 is equal to 50 kilo ohm. Okay, what will happen if you take a reasonable amount of output resistance? So Z0, okay, once again, is RC parallel with R0. Okay, that implies RC into R0 divided by RC plus R0. 3 kilo plus, sorry, 3 kilo into 50 kilo divided by 3 plus 50 is 53 kilo. Okay, so you would get Z0 as how much? How much you will get Z0?
2.83 kilo.
Correct, no? 2.83 you'll get, right? Okay. Okay, good. So, you know, since they have asked you to compare the value, so you can say that with R0 is equal to 50 kilo ohm, Z0 is reduced. Okay, it is not appropriate. Z0 gets reduced from 3 kilo ohm to 2.83 kilo ohm. Okay, that means to say slightly the output impedance gets reduced due to the effect of, you know, finite value of R0. Okay, so slightly it gets reduced. Okay, that means to say even your output voltage should also be reducing. Okay, let's see. A. So this is your part A of fifth, and this is part B. AV with R0 is equal to 50 kilo ohm. Let's see how much you'll get the voltage gain. So voltage gain AV is basically minus RC parallel with RE, R0 divided by RE. Okay. So how much you'll get? Minus RC parallel with R0. Kilo divided by 10.71. How much you'll get?
263.3.
Minus 263.3.
3.
Okay, 63.3. Okay. So what is the conclusion for AV? By how many units the voltage gain has reduced? See, the earlier voltage gain was negative 280 and the present voltage gain is negative 263. So, you know, with R0 is equal to 50 kilo ohm, the voltage gain has, dipped or reduced by an amount of roughly say 17 units. You can say by 17 units. Okay, why I'm saying units? Because voltage gain is dimensionless. Okay, so this is the problem. Okay, so each part can get you about say 2 marks each. So this will have 2 marks. Okay, and this will have 2 marks, and so as these 2 parts, 2 marks and 2 marks. Okay, so normally it will come for 8 to 10 marks. Okay, fine. So the same process is used throughout the circuit, whether it is RE model or H model. The same idea is used, okay, to determine Zi, Z0, AB, and AI. Okay, fine. Let me take a brief pause here. Just want to understand. Did you understand? Did you understand this?
Yes, sir.
Yeah, frankly, you should say. If you don't understand, I can take a special class and I can redo the stuff. But I want proper confirmation from your side, whether you have understood or not, because I cannot see you from the other side, right? Because I can't see you whether you have really understood or not. Okay, I have to just believe your words. Okay.
Understood,
No,
sir.
yeah, if no, please feel free to ping me. I can arrange for a special class. Okay. So can I have some yes or no in the chat box? If understood, yes. If not understood, I'll assume that you haven't understood, and I can arrange for a special class. Okay. Okay, fine, fine. All right. Next task is your voltage divider bias circuit. So what I will do, I will draw the circuit, okay, and I will, ask you to propose the RE model for the same. All right, fine. So voltage divider bias circuit. Okay. In the sense, amplifier based on voltage divider bias circuit. Okay, let's look at it. RE, because if you understand voltage divider bias circuit analysis, you can do it for emitter bias because both are the same basically. Only the difference is that you will find 2 resistors on the input side. Okay, that's VCC for you. This is R1. This is R2. Okay, and yeah, so this is collector, emitter, and base, and this transistor will have some, beta value or HFE value. Okay. So that's your base terminal, and the input capacitor CI, okay. The input signal VI, output capacitor C, and the C0, okay, and the output voltage, okay, that is measured from this end of the capacitor and the ground. So this is your voltage divider bias circuit based common emitter amplifier. Okay, so what you have to do is you have to find the RE model. So first step is to find RE model. And in the second step, you determine ZI, Z0, AV, and AI. Okay, fine. So let me. Fine. So 5 minutes are there. I don't want you to, do this today. I'll do it tomorrow. No problem. Okay. So what I'll do today, I'll circulate a quiz based on fixed bias circuit. Okay, or probably I can include a voltage divider bias. Okay, what I will do today's quiz, I'm telling you the portion now only, going to be on voltage divider bias circuit. Okay, so based on voltage divider bias circuit, we will have certain quiz questions. Okay, fine. You can take a break. If you haven't answered the attendance, you can type your attendance. Okay. Okay, now what I wanted you to tell you is that, you see, I follow something known as Google Meet, okay, wherein I get your log. Wait, let me